In this video, we're going to go through some of the factors which stabilize different resonance forms. So we're going to try and understand here what makes one resonance form more stable than another. So we'll go through about 5 different factors, and this is going to be one of the most important factors to evaluate. So I'm going to draw out 2 resonance forms here, and we'll start off with this ketone, and we'll draw a resonance form for this ketone with its resonance form here with a CH3 and a CH3 here. So what we've done is we've taken this pair of electrons in the carbon-oxygen pi bond and we've moved them up to the oxygen, so now the oxygen has a negative charge and the carbon's got a positive charge. And the question is, which of these 2 resonance forms is more stable? And a good rule of thumb in organic chemistry and chemistry in general is you want to minimize charges. The lower the charge density, the more stable a molecule is. So the less concentrated charge is, the more stable. So by that token, the molecule, or I shouldn't say molecule, but the resonance form on the left is going to be more stable, and the one on the right is going to be less stable. Okay, so let's look at a slightly different example. Let's take carbon with CH3 and put in alkene here, and let's draw the resonance form for this molecule. So let's say that we broke this bond and we put a positive charge over here. So CH3, CH2, and this now has a pair of electrons on it. The carbon has a positive charge, this carbon has a negative charge. Again, which of these 2 is going to be more stable, this resonance form on the left or the resonance form on the right? Well, again, this is neutral, so this is going to be more stable, and the one that's charged or has charges on it, it's going to be less stable. And we should note that the net charge, actually in this case, is still 0 because the negative and positive cancel out. So, I mean, the net charge hasn't changed. The net charge is still the same, still 0. Net charge equals 0. But because it has these point charge, we call point charges, so each atom bears a formal charge. This one bears a formal charge of +1, this one bears a formal charge of -1. This is going to make it a less stable contributor to the resonance hybrid. It's not, or less important contributor to the resonance hybrid. It's not going to be as important. So this one on the left is going to be more stable. And then let's look at something slightly different. So let's take this nitrogen here, and this is called the azide ion. You might see hear people pronounce it azide. It's really potato. And we can draw 2 different resonance forms for this. And this has a plus charge, this is a minus charge, this is a minus charge, that is a plus charge. Now what's interesting about this is this actually bears a charge of -2. So the net charge is -2 plus 1 is still -1, and the net charge here is still -1. But which of these 2 resonance forms do you think would be more stable, the one on the left or the one on the right? Well, the one on the left has this nitrogen which has a charge of -2, which is very, high charge density. Which is going to make this pretty unstable compared to when we have charges of -1 on each of these nitrogens. There's definitely a lower charge density. So they're going to be more important for the resonance contributors. This is going to make more of a contribution. So more stable, and so that's less stable. Okay, so really the bottom line from this video is just that what's going to stabilize your resonance contributors is the less charge the resonance contributor, the more stable it will be. Okay, so minimizing charges when possible. So obviously neutral is going to be more stable than a species which bears positive charges. And if you have a choice between having a charge of -2 on one atom versus spreading that -2 charge over two individual atoms, then that is going to be a more stable situation. Okay, so that boils down, that's the first factor when we're evaluating resonance forms, and in the next video we'll talk about a factor which involves electronegativity.